Hi everybody. Today we're going to look at Google's Universal Sentence Encoder. So this is basically a NLP deep learning model from Google that you can download and use. I'm going to show today. That's basically better than Bag of Words or Word2Vec. So Bag of Words, you one hot encode the words and then you pass that off to your machine learning algorithm. Word2Vec, you produce embeddings by trying to predict the word given the context words, so the surrounding words, maybe the five to the left and five to the right of the middle word that you're trying to predict. So words that have similar contexts are mapped to similar vectors in the vector space. So that provides some semantic meaningfulness. Then um, you have these types of models which try to basically predict the next set of words given the prior words. So Universal Sentence Encoder is such a model. There are some variations in it and other models that are like it, such as BERT. Um, but basically, these provide encodings over not just words, but maybe sentences, phrases, and perhaps even longer pieces of text. And the idea is when you train these models, you're training them on some downstream task that is semantically meaningful. And as a result, the word embeddings that you get out of the model are also semantically meaningful. In other words, if you had two sentences that were similar semantically, and you pass them through the encoder, it produces a vector representation for each of those two sentences. If they truly are similar, then those two vectors will be close to each other in the vector space. And if the two sentences are semantically different, they would be farther away from each other in the vector space. So this is just one of the models that I'm showing here today. Again, it's the Universal Sentence Encoder. So everywhere you see USE, that's what it stands for, Universal Sentence Encoder. And so I have the code for this in my repo. You can see in the description. But basically, what I'm doing right now is I ran this script right here that I have. That's in the repo. Download use.sh. I have it open here in VS Code. But basically, it's just a command that you can copy paste if you want to do it that way. But it fetches the model at this endpoint, and then it unpacks it and puts it in a folder called USE on my local machine in my current directory. So when you're first doing this, you want to create this directory. Just do make dir USE, and then run this command, and it'll put the model into this folder. If you don't have this created, it'll complain at you. But all you have to do is literally create it, right? So it takes about maybe 5 to 8 minutes. It just finished for me. It says total time spent 6 minutes. So if I do clear ls, this is the folder. Again, if you're trying to download the model, do make dir use. That'll create that, and then run. So it'll be like this, and then you will run this script in this order. Obviously, you can add, if you want to add make dir up top here, you could totally do that. But whatever way you want to do it, you can do it. So if we go into the USC folder, we'll see this is the model, and it has some other stuff that comes along with it. We don't have to worry too much about all that stuff right now, because all we're going to do is just use it. So if we go over to this file, I have usc.py. This is a script I wrote that will allow us to use it. So you can see I'm going to go through line by line, but basically we have our TensorFlow and our TensorFlow hub that we're importing. Here are the versions of the packages. You have to do this, so you have to go with version 1 for compatibility with this. So I'm not sure why TensorFlow has some description on there. You can read it yourself. And then I have these other packages here just for some handy stuff. I'm going to do some visualization. And here are the versions if you want to download them yourself. If you want to download any of these packages, you'll do a pip install. And let's say you want to download TensorFlow 2.0.0. You would do pip install TensorFlow equals 2.0.0. Very simple. If you're using Python 3, you would do pip3 install TensorFlow 2.0.0, etc. And then if you want to, if you want to install the stuff in a virtual environment to keep it separate from the rest of your machine, you can install Python virtual environment and then run this command, and this will create a virtual environment called venv, and then you would just source activate it, so vn-bin activate. You would do something like this, and then you could pip install everything into that virtual environment, but I'm not doing that now. I just have it all on my machine ready to go. So that's all the packages. We got NumPy, Seaborn, Matplotlib, and Pandas. And let's get to the core of this. So the first function I have here is loading the Universal Center Encoder module. So it's just a function to load it. So I got this from some blogs, just a couple blogs I was reading. This works fine. So you do some TensorFlow magic, and then you end up with a lambda function expression that you can use to encode some stuff. So next line below, I'm using the loading function here to go and fetch the model from where we just downloaded it to the USE folder in the current directory. And then I save that to Encoder. Encoder is what we're going to use to execute the encodings. So next I define some messages. So just some phrases, some sentences. I love pets. I like dogs more than cats. We can kind of expect that hopefully these will somehow be similar to each other. I have a few other sentences, just I once had a bird but it flew away, just some random thing I wrote. I like chocolate more than vanilla. This, because I'm saying I like something, maybe it will be somewhat similar to I like dogs more than cats. We'll see. I have airplanes scare me for some reason. I have always been afraid of flying. These should be scored as similar. You can see that, this has scare, this has afraid, this has airplanes, this doesn't. This has flying. So they're written in very different ways, but they mean the same thing, kind of. So we'll see how it does. The last one is an interesting one. I love school versus I hate school. So they're both about school, but one is loving it and one is hating it. So we'll see how the encoder does there. I don't know if it will be scored as similar or not similar. But those are our sentences or phrases that we want to encode. The next step is to actually do the encodings. So we take the encoder and we pass the messages, which is a list of strings, as input, and we get out encoded messages. And then we can print them to the screen if we'd like to. What you're going to see is just a NumPy array, and its dimension is going to be, I have 8 sentences here. It's going to be 8 by whatever number dimension the encoder puts out by default. I think the default is 512 dimensional. You can change that. A lot of, even Word2Vec has different length vectors for the embeddings. Next, here, all I'm doing is I'm initializing a empty data frame, and I'm just going to store all the similarities so I can visualize them with Seaborn. That's all this is. So I iterate over all the messages, for I, for j in the messages. What I'm going to do is then calculate the cosine similarity. So here's the mathematical formula for it. If you're familiar with vector calculus, you should remember this. So the cosine of the angle between the two vectors x and y is going to be equal to their dot product divided by the product of their magnitudes. That gives you the cosine of the angle between them. And yes, higher dimensional vectors do have a concept of angle, this theta. But really what we're after is this cosine theta. The cosine theta is the similarity. It's a number between -1 and 1. Okay, so let's see. So the next thing we do is we take the dot product. You can do it lots of different ways. You can do np dot and then pass the two vectors in. Remember, encoded messages is the vector, that we got from the encoding right here. So these are the encodings. So we get the encoded messages for the ith message and for the jth message. Take their dot product. That's our dot product. That's going in the numerator here. Then we get the magnitude of the x vector and the magnitude of the y vector. Here I have that in the next two lines. The magnitude of the ith message and the jth message. Really, the magnitude of a vector is just a dot product with itself. That's why you have encoded messages I here twice. Take the dot product and then you take the square root to get the magnitude. Finally, you calculate the cosine of theta using the formula that I have commented out here, and you're done. So now after iterating and we save all of this, we append it to the empty data frame. And then once we're done with that, we go ahead and convert. We do like a little pivot table, and we convert it into a heat map that we can then directly pass into seaborn.heatmap and generate a figure. So let's run this now. Python 3, and we're going to run use pi. So it's going to load up the TensorFlow model, and then it's going to execute the code. So you can see below here that a numpy array got printed out. This is because I have that line in the code that prints out the encoding. So you can see it's a numpy array, and you can like look at this in different ways if you'd like to when you're doing it, on your own. But let's look at this. So this is the heat map. So it's a heat map of the pairwise cosine similarities between the messages. So let's look at this. So if you're bluer, darker blue, that means you're closer to 1, right? So that means that you're very similar or exactly the same. And if you're closer to light colors, then you're very dissimilar. So that makes sense why the diagonal is all 1s, because they're the same exact sentence. I hate school. I hate school. I like chocolate more than vanilla. I like chocolate more than vanilla. So they're all going to be dark blue to 1. Let's look at two things that we think should be similar, and let's see if they are. So I've always been afraid of flying, and airplanes scare me. So let's look at airplanes scare me on the y-axis, and on the x-axis let's look for I've always been afraid of flying. So that turns out to be the top right corner. So the top right corner is the similarity between airplanes scare me for some reason and I've always been afraid of flying. As you can see, they're very dark blue, so they're close to this, it looks like to me, this 0.8 number, so they're being scored as similar. Makes sense. Now let's look at, say, I love pets, and let's go along until we get to I love school. So they're kind of similar. One's about pets, one's about school, but they're both saying they love it, so that explains why it's kind of like a light blue, which is around this 0.6 number. So they're kind of similar, right? That makes sense too. Now let's look at I like dogs more than cats, and I love pets. So if I go I like dogs more than cats, I look for I love pets right here. So these happen to be actually on the darker blue side, meaning that they're similar. And that makes sense. They're both saying they love animals. So that's another good example that it's working. Now let's look at something that shouldn't be similar. I hate school, and I once had a bird, but it flew away. So I hate school right here. I once had a bird and it flew away. So that's on the much lighter side. So obviously it's flagging it as being different. So there you go. That also makes sense. And then if we look at maybe I love school and I hate school. So let me look for I hate school, I love school. So these are being scored as pretty similar because they're both about school, although one is saying I hate and one is saying I love. So maybe this is not what you wanted out of your model, And that's why it's good to know how the models were trained. If you trained this model on a data set such that the downstream prediction task was to decide if two similar sentences had different verbs in them, your embeddings would reflect that, and it would show when you would do a cosine similarity. So it's good to keep that in mind. But that's pretty much it. So you can use this in your machine learning modeling tasks, whether it's clustering or supervised learning. I love the quality of the encodings you get from this. I'm sure they're comparable or maybe better compared with BERT. That's another popular one. But a lot of times this seems to be sufficient for the projects that I've worked on. But yeah, I think the field is growing. It's getting bigger and bigger with regards to NLP, and text encoding is right at the center of it. So I think better and better encoding methods will come out. And obviously the perfect scheme is if you do the training on a text data set that is semantically meaningful in a way that fits your use case. But it's hard to train these models. They're very big, they're very complicated. You need parallel computing, and you probably need a good amount of money to train these. But yeah, so that's it for today. Make sure you check out the code in my repo in the description. I have the link there, and I'll talk to you guys next time.